Okay, ladies and gentlemen, we are in our quadratics unit and we're in lesson 6, building quadratic functions to describe situations, or mainly using quadratic functions to model a word problem. So we're looking at problem 6.1, skybound. So in reading the problem, a cannon is 10 feet off the ground and it launches a cannonball straight up with a velocity of 406 feet per second. Imagine that there's no gravity and that the cannonball continues to travel upwards with the same velocity. So I imagine, Pirates of the Caribbean, and I imagine, pirates with a cannon, and they shoot it straight up in the air, which isn't very smart. It's probably going to come back down on Earth. However, in this situation, we see there's no gravity. So I see that we have 10 feet off the ground. That seems important. And the velocity is 406 feet every second. So in looking at completing the table, I see that we are constantly adding 406 every second. So I'm going to pull out my calculator, clear out what's in there. And we have 10 feet, and I'm going to add 406. And I see after the first second, I'm at 416. Then I'm going to add 406 again. And I see after the second, we're at 822 feet. Then I add 406 again. And we're at 1,228 feet. I add 406 again. And we're at 1,634 feet. Adding 406 again, we're at 2,040 feet. And we need to come up with an expression for t. So I'm going to look here, and I notice my rate of change is constant, and we're always adding 406, which means it's linear. So if I'm always adding 406, we could repeated addition is multiplication. So I could take 406 and multiply it by t. However, after I look, 406 times 1 is not 416. I forgot that the cannon is 10 feet off the ground, so I need to add that 10 feet. So I'll put a little tail on the t so that you can see that that's a variable. So again, this is an expression for the distance. And now we need an equation. So for my equation, distance in feet is d, and the t is time in seconds. So all that I need to do is put a d equals by my expression. So d is equal to 406 t plus 10. And now we need to answer this question. What's the rate of change? So down here, my rate of change is 406 feet per second. And again, rate of change is the same thing as your slope that you learned in 8th grade math. And then what is your y-intercept? Well, your y-intercept is your starting value. So our y-intercept, or again, our start, is 10 feet. So again, what does it represent in the problem? That 10 feet is our starting height. So we know that we're on Earth and that this would not happen. Otherwise, this cannonball would shoot up indefinitely. It would keep going into space. Maybe it would hit the moon, maybe it would hit the sun or one of the other planets. But we know that this would not happen on Earth because of gravity. So we're going to track the real height of the ball. So earlier we completed a table that represents the height of a cannonball in feet as a function of time if there was no gravity. So here I'm looking, and this table shows the actual height at different times. So we need to compare the values in this table with the ones we did earlier and make at least 2 observations. So I'm just going to look at the values. At 0 seconds, they're both at 10. One observation that I can make from there is the starting height is the same. And then here, for no gravity, the height after 1 second would be 416, but it's 400. And then here, 822, but after 2 seconds, it's 758. And just comparing all of these, I can see the real height is a little bit lower. So I could say the values in table 2 are lower than table 1 because of gravity. And then another thing that we might notice is comparing our rate of change. So here, to go from 10 to 400, we see that we would go 390. Here, from 758 and subtracting 400, I won't need a calculator here. I can just do the 7 minus 4 and get 358. But I can see here, just working on the first 2, that the rate of change is not constant. So the second table is not linear. So now we're going to go on. And what I want you to do is graph both of these. And you have to compare how are the 2 graphs alike, how are they different. So again, on here, you're going to have to get used to estimating. I see that on the first graph, after 0 seconds, it's at 10. Going back for 1 second, we have to go to 416. So 1 second, I go and have to estimate. Well, maybe 416 is about right there. And 2 seconds, I'm at 822. So 822, I'm going to estimate to be about right here. And then 3 seconds, I'm at 1,228 feet. 4 seconds, 1,634. And 5 seconds, 2,040. Now the cannonball is moving between these between the intervals from 0 to 1 second. So it does make sense to connect these. And then I notice that the first graph is linear. And now we're going to do the second graph, which again starts at 10 feet. And then for 1 second, it's 390, which I know is just a little bit below the 400. So I'm going to just put that a little bit below. And then we're at, oh, I'm sorry, it should have been at 400. My fault, I misspoke. And then here, 758. So here, again, I'm just going to estimate a little bit lower. And then 1,084, just a little bit above the 1,000 mark. Again, I'm estimating. And then 1,378. So again, around right here. And then 1,640, that's going to be above the 1,500. I estimate that to be around right here. And then what I notice about this is it is a curve. Now, from previous lessons, we learned that this is actually the effects of gravity. So gravity on Earth has a very specific formula, but it would be the height is going to be y equals negative 16 x squared plus v naught times x plus s naught. And v naught is our initial upward velocity. And s naught is our initial height. So in doing this, in substituting in our numbers, we know that our initial velocity here, going back to the first problem, was 406 feet per second. So y is going to equal negative 16 x squared plus 406 x, and our initial height was 10. So let me box that in to keep that kind of separate so that that stands out. And if this graph was a little bit upsetting to you, let me show you how to use technology to graph that. So what I'm going to do is press y equals, clear out what's in there. And the first graph was linear, so y equals 406x plus 10. And then the second graph was y equals negative 16x squared plus 406x plus 10. Now we need to change our window to match here. So I'm going to go to window. The x minimum, we're going to go from 0 to 10 seconds. And we can count by ones. The y minimum is 0 to 2,500. And we're counting by 500. So this y scale, change it to 500. Press graph. And again, the first one's linear. The second one we can see curving off. So now we have another function. The function defined by d equals 50 plus 312t minus 16t squared gives the height of a cannonball t seconds after it leaves the cannon. So what did the 50, 312, and 16t square stand for? So if you look here, they just reversed everything, but this 50 is my initial height. So I'm going to write that up here. So 50 feet is the initial height. And then we have 312 feet per second would be my initial velocity. So 312 feet per second is the initial velocity. And then the negative 16t squared is the effects of gravity, or my acceleration due to gravity. So the negative 16t squared is gravity. So now using technology to graph the function, we have to adjust the window to the following boundaries. So again, I'm going to put in my function, pressing y equals, clear everything out. So our function here, we have 50 plus 312x minus 16x squared. And then we just have to change our window for x from 0 to 25. So I'm going to press window. X min is 0. I'm going to change the x max to be 25. I'm going to change that scale to counting by fives. And then the y min is 0 to 2,000. And I'm going to have it count by 250. And then graph it. And again, we see that the cannonball goes up and then comes back down. So the shape of the graph is curved. So the shape is curved. We have learned that the graph is called a parabola. And then what does that mean? That means the cannonball goes up and then comes back down. So now to estimate the maximum height, we can actually use technology to figure out, well, what's the y coordinate right here of that vertex? So to do that, you can press second calculate. We're going to go to the maximum level. It says left bound here. So going to the left of the maximum, we hit enter. And then going to the right of the maximum again, we hit enter again, hitting enter a third time. We see that after 9.75 seconds, the height is 1,571 feet. So we can say with precision 1,571 feet. And then over here again, we have to estimate when does it hit the ground. This can be done in a couple ways. You can hit trace and move our cursor over. Now, when it hits the ground, it's not the height. We need the height to be about 0, which you notice we go from 47 to about -12. It seems like it's going to be around 19.5 seconds, but we're not sure. Again, we can get more precise by going second calculate and then go to 0, go to the left of the 0, and then go over to the right of the 0, hit enter a couple times. And we see that it happens at about 19.66 seconds. So what's the domain of this function? So the domain is the x values. And we can see the domain is between 0 and x is between 0 and about 19.66. And it can be equal to both. So we'll put in our less than or equal to's. Or another way to say that is just using that interval. So 0, 19.66. And then just a further question to express our range. So the range is, we went from, our height went from 0, and then that's a y values, to 1,571. So we just put our less than or equal to's there. And then to express it this way, we would say y is between 0 and 1,571 feet.